Alrighty, so with the basic rule of counting permutations and combinations, in particular in combinations, we talk about the binomial theorem, okay, where you have two outcomes and then you're able to choose them. Now we're able to generalize it to a multinomial coefficients and also a multinomial theorem that is related, okay? So to get us started, I want to start an example. Suppose a police department of 10 officers wants to have 5 of them patrol streets, 2 of them doing paperwork, and 3 of them at the donut shop. I guess everyone wants to be at the donut shop. How many ways this can be done? Okay, so this is, if you can see that, if we think about it in the context of experiment again, okay, we have this experiment and we have 10 officers. We have to choose 5 of them to do one task, 2 of them to do another, and then 3 of them to do the last one. So without the jargon of multinomial coefficients at this point, if we want to complete the task, what can we do? The first part of this is to choose the 5 officers to patrol the street. Okay, so that, well, is a choose function, 10 choose 5. Okay, so we're done with that. And the next step, well, is once we have chosen the 5, we have 5 remaining, right? So if we want to write it, is 10 minus 5. And we are choosing 2 of them to do the paperwork. Okay. And the last one, well, we know that we have remaining 5 minus 2, and all of them will be at the donut shop, right? So it's to write it more completely, this is what we do, but then we can quickly reduce this into 10 choose 5 times 5 choose 2, and then times 3 choose 3. Okay, 3 choose 3 is, we know, one property, right? N choose n is always 1, so that goes away. Okay, well, it's 1, so it's straightforward. And let me show you, once we have broken it down into using the, this is using the combination definition, the choose function, and break it into all of the factorial notation. And we start to see that we're able to cancel out certain things, okay? So this 5 factorial can cancel out with this 5 factorial. And then this is actually another 5 factorial. So in the end, we have this 10 factorial divided by 5 factorial times 3 factorial times 2 factorial, okay? So this, if you remember, one of the permutation scenarios that we talked about, right? If we have n objects and we have all of them, remember, some of them in one group, some of them in another group, and then the total number of permutations in that kind of scenario actually is the same results, is n factorial divided by n1 factorial and 2 factorial, etc., etc. Okay. However, here, notice that we're not doing permutation, okay? We are in not caring about the order. As we know, back then permutation always cares about the order. Now we're really just like grouping, right? We're grouping 10 objects or 10 officers into 3 different groups, okay? And we're trying to figure out the number of ways to do that, okay? So from here, we're able to introduce the multinomial coefficient, okay? So generically, let's look at the question. 10 officers, they're all different from each other, okay? So we have a set of n distinct or different items or objects, and we want to divide them into r distinct groups, okay? So in this example, we have 3 groups, right? 1 for patrolling street, 1 for paperwork, and then 1 for donut shop. So we have 3 distinct groups of respective sizes, and we're given what the sizes are, right? 5 for the first, 2 for the second, and 3 for the last. So the number of possible divisions, which is actually a multinomial coefficient in this case, is defined, well, notation-wise, we have this really tall and wide choose function. You have the total number, the number of distinct items at the top, and then you just list all of the group sizes, okay, in the bottom with comma separating them. And by definition, well, this is the number of possible divisions, and we have to see, well, you can cancel out all of the intermediate terms that you can imagine, and then you are reduced to n factorial divided by the product of all of the size factorials, okay? So, like I said before, you can always start with a particular example to understand why that is the case. But then from this particular example, we have seen those cancellation, and you can see that if you have so many items in between, they're going to get canceled out like one by one. So eventually, you're always going to get n factorial, right, divided by the factorial of each of the sizes that we're doing. Okay, so this is multinomial coefficients, okay? And what we're doing is we're trying to divide n distinct items into r distinct groups, and we also know the sizes for each group. And in particular, I should highlight that, well, the size, all of the size should add up together to the total number of items you have. Okay, so multinomial coefficient, and then, well, this is, like I said, you can really, if you go back to the officer examples, we know that, well, we're really choosing one group at a time, right? And then for each case, you're subtracting whatever you have chosen from the total that you'll be able to choose from for the next step of the choose function. So that's why later on you will see that many of them get canceled out, and then you get the final result is what we have seen before. Okay. And well, multinomial is what we were talking about earlier, is a generalization of the binomial. Okay, binomial, you have two outcomes. Here you have more than two. So if R, which is the number of groups that we're talking about, is 2, this binomial, this multinomial coefficient actually reduces to the binomial coefficient. Okay, it's just the choose function itself. Okay, so this one, as we know, if we follow the definition from before, this will be n choose n1, right? And then the remaining is n minus n1 choose n2, okay? But this whole thing we know is n2, so n2 choose n2 got canceled out, it's 1. So, well, it is reduced, as we can see, to the binomial coefficient. And don't forget that the sum of the n1 and n2 needs to be n. Okay, and lastly, we have binomial theorem, right? So we also have a multinomial theorem. It will be a little bit less, I guess I should say, less intuitive and more challenging to understand why exactly the case. But just to give you the example of why this could work. So remember the license plate example we used for introducing the binomial theorem, right? We have a plus b to the power of n, okay? And we know that a is the number of letters you can choose from, b is the number of numbers you can choose from, and then you have n digits that you can do. So the left-hand side back then, what we're showing you over here is the number of distinct license plates you're able to have. And the right-hand side, if you remember, we're breaking it down into each case, each of the cases where we're considering exactly k number of letters in that case. So now generalize it to the multinomial theorem. Maybe one way we can think about it is that, well, instead of only having 2 choices for the license plate for each digit, let's just say we can choose from 26 capital letters, okay? And let's just say we can choose from 26 small letters, and then we can also choose from 10 digits, okay? So, okay, this is the case, right? That, well, in addition to capital letters and the numbers, we can also choose small letters. So the left-hand side, as you could imagine, now it's going to be 26 plus 10 to the power of n, which is the number of digits. The right-hand side, of course, well, again, it's more involved as what we're talking about as before. But again, as you can see that the summation is, again, looking at the sum. Well, in our case, we have 3 groups, so r equals to 3, right? So we're looking at the sum, and then you can think about each of the terms in the sum will be a exact number of combinations of the, like say, exact like n1 and n2 and nr number of, well, in this case, let me just say out loud, n1 will be the number of capital letters, right? N2 will be the number of small letters, and then we only have an N3, which will be the number of digits, the number of numbers to be used in the digits. So, well, and then we have this, if you remember, the multinomial coefficient, that's a sequence of choose functions. So the right-hand side in sum is trying to also show you that, well, the total number of license plates can also be deduced by counting exactly a particular combination of the 3 numbers that you're able to come up with, add up to n, and then each of this is a choose function times those powers together. Okay, so not surprisingly, like what we have seen before, if r equals to 2, this is a binomial theorem. So binomial theorem is a special case of the multinomial theorem. Okay, so multinomial theorem and then the coefficient overall, they're really useful when you're dealing with more than 2 groups, like, oh yeah, more than 2 groups in this case. So I'm sure you will be encountering different exercises and examples of doing this. And so make sure that you not only know the form, like the expression of the multinomial coefficient, but also why we're able to come up with this, and then why the computation works in the way that it is.